Welcome to Module 8, the final module, Prolog as a knowledge engine. Over 7 modules you learn the parts of this language. Facts and rules, unification, backtracking, recursion, and the control you gain from cut and negation. Today we put them together. We will see that a Prolog program is not just code, it is a knowledge base with an inference engine built in. And we will use it to build 2 real systems, a world you can explore, and an expert that can diagnose. Let us step back and name what we have. The facts and rules you write are a knowledge base, a declarative description of a world. Unification and backtracking are an inference engine that searches that knowledge for answers. Recursion lets you walk nested structure, and cut and negation let you control the search and reason about what is absent. Put together, the whole language is a knowledge engine. You describe what is true, and Prolog works out what follows. This is the heart of declarative programming, unlike Python, where you spell out every step. In Prolog you state what holds and let the engine find the how. Underneath, 3 pillars hold this up. First, knowledge representation. Everything is written as horn clauses, simple facts and rules. Second, the inference engine. Prolog proves goals by unification and resolution, matching and reducing them automatically. Third, the solving strategy, a depth-first search of the proof tree, with backtracking to exhaust every alternative. Representation, inference, search. Master these 3 and you understand how Prolog turns a description into an answer. Resolution is simply that, repeated, take a goal, find a matching clause, and replace the goal with the clause's body, until nothing is left to prove. Here is our first system, straight from a classic example. A 3-year-old wants to sleep, but she cannot settle without her blanket, called Nanny. The blanket is hidden in the washing machine, and to search the dark house she needs a flashlight from the desk. This is a little world of rooms, doors, and objects. Our job is to describe that world in Prolog, and then let the engine reason about how to move through it. We start with facts, the world model. Each room is a fact. Each door connects 2 rooms. Each object has a location, the flashlight is on the desk, the blanket is in the washing machine. With just these facts we can already query. Ask what is edible in the kitchen, and Prolog unifies your query against the database, then backtracks to find every match. Facts plus unification already give you a queryable knowledge base. And queries run in any direction, the same location fact tells you what is in the kitchen, or where the apple is. Rules turn that database into knowledge. A rule says where to find food, something is food in a room if it is located there and it is edible. Give a predicate 2 clauses and you get an or, food is anything edible, or anything that merely tastes yucky. And to make a one-way door work both ways, we write connect with 2 clauses, 1 for each direction. Facts plus rules equals knowledge plus the power to infer. Notice the pattern, a predicate with several clauses is simply a logical or, and the engine tries each clause in turn. Now watch the inference engine reason. Objects can be nested, the key is in an envelope, the envelope is on the desk is in the office. Ask, is the key in the office, and there is no direct fact. So a recursive rule takes over. Is the key located here directly? No. Then is it inside something that is here? The engine descends, desk, then envelope, until it lands on the fact, the key is in the envelope. Success then propagates back up the chain. That is goal reduction, a query unfolding through rules until it reaches facts. A knowledge base need not be frozen. Prolog can change its own database at runtime. Asserta adds a clause to the front of a predicate, retract removes one. This is how the game remembers where you are. To move, we retract the old here fact and assert the new one. One caution, carried over from cut, backtracking does not undo an assert or retract. These changes are permanent side effects, so use them deliberately for state, not for ordinary logic. This is exactly what lets a text adventure work. Go to a room, look around, take an object, each command quietly rewriting the database. Our second system is an expert. We will build a small medical diagnosis engine, and it has 3 layers of knowledge. At the bottom, symptoms, entered as facts about a patient. In the middle, disease rules that recognize patterns of symptoms. On top, treatment rules that follow from a diagnosis. Reasoning flows upward, from symptoms, to a disease, to a recommended treatment. This is exactly the predicate logic you have been writing, now doing a specialist's job. Let us run a diagnosis. The patient has fever, cough, and headache, 3 symptom facts. The flu rule requires exactly those 3, so it fires, and the engine concludes flu. Then the treatment rule built on flu fires in turn, recommending rest and fluids. Watch the cold rule, though. It requires cough and sore throat but, crucially, the absence of fever. Because fever is present, negation as failure blocks it. What you see is a knowledge engine reasoning, symptom, to disease, to treatment. Here is the knowledge that drives it. A disease rule is just a conjunction of symptoms. The cold rule uses / plus fever, the negation as failure from Module 7, to say, only if fever is not recorded. Remember the closed world assumption, a symptom not in the database is treated as absent. Treatment rules form a second layer of inference on top of disease. And to list every possible diagnosis, we use a fail-driven loop, print 1, force a failure, and let backtracking drive the engine through the rest. We can even make it interactive. A recursive loop reads symptoms one at a time, asserts each as a fact, then runs the rules to print a diagnosis. Step back and place Prolog among the ways we represent knowledge. Prolog uses logic, facts and rules, reasoning by automatic backtracking, powerful and concise, but weaker at probability and scale. Production systems use if-then rules with forward or backward chaining, very explainable, but they do not learn. Semantic networks use nodes and edges, intuitive but limited in what they express. Knowledge graphs use triples at massive scale, yet their reasoning stays shallow. Each method trades expressiveness against efficiency and learning. It is also why Prolog struggles with uncertainty. It answers yes or no, not how likely, which is just where probabilistic and learned methods take over. Where does this lead? Prolog's great strength is that its reasoning is explainable, every answer comes with a proof. Modern neurosymbolic AI aims to marry that with the learning power of deep networks, logic for what must be true, learning for everything else. One concrete form of it puts a logic engine as a verifier around a large language model, checking each answer against hard rules, so the system is not only fluent but correct, consistent, and current. The knowledge engine you built today is the seed of that idea. That pairing, explainable logic with learned perception, is widely seen as a path to the next generation of AI. And that completes the journey. Across 8 modules you went from your first fact and rule, through unification, backtracking, recursion, lists, the order of search, cut, and negation, to building real knowledge systems. You can now read a Prolog program, write one, reason about how it searches, and use it as an engine for knowledge. Where it goes next is knowledge graphs and large language models, the modern face of knowledge representation. Whatever you build next, the instinct you have gained, to describe a problem as facts and rules and let a machine reason, will carry over. Thank you for working through LectureCast Prolog. Go build something that thinks.